Hello, everyone. Today I'm going to introduce disjoint sets, and this is the final report in DSAP. This is an illustration of disjoint sets. Now let's think about a problem first. If I'm a boss and I want to sell tickets for a competition or a concert, there are different zones with different prices. And now we need to be clear about who is in which zone and to sort the spectators very efficiently. And our solution is disjoint sets, because in this situation, disjoint sets will be efficient and due to its easily sort specialty, and also it can be easily merged. Like, for example, this is an NBA sorting system, and if we want to combine courtside with sidelines spectators together into the same zone, then we can just do it very easily in a disjoint set. Now let's talk about my motivation about why I choose this topic. And actually, there are advantages of disjoint sets. For example, they have a wide range of applications in the real world, which is very useful. And still, do you recall your math lectures in high school that in permutations and combinations, the teacher emphasized on sets a lot. And actually, I love the chapter very much personally because it helped me to become more logical person. Now, I want to give an overview about disjoint sets. In disjoint sets, every element should come from one exact subset. Then, if we want to check two elements are in the same subset, we can do it efficiently through the disjoint sets. Then it is mostly implemented through array or linked list. If we use array to implement a disjoint set, then it's also called a forest because each subset looks like a tree, and many sets combined together they form a forest. Then the parent node A1 and B1, we give them index like a special one, for example, a negative number to separate them from other nodes. Then the node index is just the array index, while the label is the name for each of the node. If we use linked list to implement disjoint set, then in each struct, we will have three spaces, and there will be head and tail pointer. Then head will point to the first struct, which is the root. The root itself will have two pointers and also one space storing its name. The root pointer will point back to itself, while the other child pointer will point back to the root one, so that we will know the root very efficiently. Then the other space is used for pointing to the next node. There are some applications. For example, we can find a minimum spanning tree of a graph using disjoint sets. Also, clarifying the relationship between elements will become easy. Then we can make a random mass generation, which is in this picture have shown. The register allocation is used in compiler optimization, and in the last, the unification is used in solving mathematical equations, and the five are the main usefulness of disjoint set. Now, let's recall our problem of selling tickets. We have various zones with different prices, and we want to be clear who is in which zone. The first step is to specify the functions we need. So we need find to see which zone someone belongs to. We need union to combine specific zones efficiently. For example, if we want to combine the upper level and the lower level, then we can do it very soon. Then we have same zone to check if two people came from the same zone. The second step, there are some people who want to buy tickets now, and we have to store them very wisely, and we use the unordered map in C++ library. Here, we set the four names of the zones as the key. Then, when there are people buying tickets, we set them to be the value according to the key. And here, it can be their names or their IDs, so that it will become very convenient. The third step, as people choose which the zone they want, we store them in our data in this way. For example, John is coming and buying tickets, then we set John's parent to be courtside. Besides, we add the rank by 1 here, and its usage will be mentioned later on. Now, step 4 is to write the functions we need. The function find here, we used a recursive call method to check where a person belongs to. The second function union here, we first compare which tree has a bigger rank, and we set the tree with a bigger rank to be the new root. The third function, same zone, we simply put find function here again to see if two people come from the same zone. Now let's run the code. Here is my whole work here, and we now run it to see the result. So basically, there is John and Amy, which choose the zone courtside. Then we ask, are John and Amy in the same zone? It should be true. And then there are 3 people come from different zones. Then we ask again, are John and Oliver in the same zone? The answer is false. Now we combine the courtside and the zone sideline together. Then we ask again the same question. Because Oliver comes from the sideline and John comes from courtside, the answer will become true after their combination. After this demonstration, I believe you must have a better understanding of a disjoint set. And now let's keep our PowerPoint. Are there further improvements to enhance the efficiency? Of course, you can use union by rank, which is choose the tree with a deeper rank to be the new root. And that is the reason why I keep the rank of each tree in my operation. So in this case, since rank 3 is bigger than rank 1, we set A1 to be the new root if we want to combine these two subsets. Also, path compression is a good method to flatten the tree to decrease the depth and make the find function to run faster. For example, this tree has rank 3, but if we compress it, then it can actually have only rank 1. So the find will become much faster. Now, if we analyze the time complexity of disjoint sets, then if we don't take any control, it will be linear in n, which is the element's number. Then if we take the above 2 steps, path compression and union by rank, then we can actually reduce the time to linear to a constant for a find and union function. About space complexity, because each entry requires set.log n for its parent pointer, so it takes set.nlog n to store the whole forest. But if we restrict a maximum number of nodes, the space complexity can actually be compressed to linear in n. And this is for the introduction of data structure disjoint sets. I hope you like it. And if you like it, please subscribe to my channel. No, I'm just kidding. Thank you very much for your attention.